Hello there, welcome to our science lesson today. And in today's lesson, we are going to look at a new topic, which is temperature and particle motion. This is a topic that is directly related to the topic we have been handling previously, which was talking about particles in solid, liquid, and gaseous state, which was mainly being looked at in terms of kinetic theory of matter. In this topic, we want to look at temperature as a factor that is very helpful in motion of particles. When we talk about motion of particles, we are talking about particles either in solid, liquid, or gaseous state. As we saw previously, we saw that particles in solid state do not move but vibrate in a fixed position. We also saw that particles in a liquid state, they move by rolling over each other, but for those particles in a gaseous state, they move randomly and in a faster manner. So, in today's lesson, looking at temperature as a factor that is very important in motion of particles, we understand that temperature is a measure. It can be taken as a measure on how much kinetic energy a particle has. How much kinetic energy a particle has. And just like in the previous topic, where we mentioned kinetic energy and kinetic theory of matter so much, we also discover that or find out that as we look at temperature as the basis of determining how much kinetic energy a particle has in whichever state of matter we are talking about, we also look at it as a factor to determine the speed at which the particle moves. So what are we seeing? We are seeing two things here. Temperature, how much temperature can be used to determine the amount of kinetic energy in a particle, but can also be used to determine the amount of speed, how much fast a particle moves. This particle can be in either of the three states of matter, as we have already discussed earlier. We also need to understand that due to the variation in temperatures in the various particles, we understand that particles that are at high level of temperature, at a higher temperature, they will always have more kinetic energy, and as a result, we shall have high movement. So, in summary, at high temperature, the movement of particles is faster. The movement of particles is faster. And at low temperatures, the movement of particles is slower. We are using the word faster as a comparative word. Slower as a comparative word. You don't say fast, but faster. Slower, but not slow. Why? Because you are comparing particles. Particles at different levels of temperature. So, at high temperatures, particles will always move faster, and at low temperatures, particles will always move at a slower pace. We also need to understand some fact here that you may find two states of matter existing at the same temperature. Maybe it may look a bit unique and funny at the moment, but within a short time, we shall be able to understand that. So we have a case where we are talking about a substance existing in solid state, but at the same time, same temperature, it is existing in liquid state. all those are at the same temperature. We can also have another case where we have a liquid and a gas, but they are also existing at the same temperature. Where do we get such a cases? Case number one here is when you are talking about a melting point of a substance. During melting, a solid is changing into a liquid. And in our second case, this is boiling, where a liquid is changing into a gas state. If it is, for example, water, we have ice cubes, which are a solid. As you expose them to a hotter condition, room temperature, it will start melting. During that process of melting, the temperature at which the change of state is taking place is usually constant. And for water at sea level is usually 0 degrees centigrade. For the case of boiling, we are having water, a liquid, turning into vapor, steam, which is a gas. At sea level, this is done at 100 degrees centigrade. Now, when you look at these two states of matter in terms of motion, this solid has particles. These particles need to move. This liquid has particles. These particles need to move. And you have just said that temperature is a measure of how much kinetic energy a particle has, or how fast the particle is going to move. Then here we are in a state of comparing how much in terms of movement is this solid or this liquid particle be having at the same temperature. This one being a liquid will have more energy, and therefore it will have more or higher movement than a solid, even if the temperature is the same. The same applies to this. Even if it is 100 degrees centigrade for both the liquid and the gas, which is steam, this gas will have more, the gaseous particles will have more kinetic energy, meaning that they are at a higher rate of movement, higher speed of movement. They move quickly, they move faster than in a liquid, even if the temperature is the same. To further understand this, we shall have to look at some other explanation for us to understand why is it that the temperature is the same, but the energies are different. The temperature is the same, the energies are different. We shall require to have an overview of partly what we have been covering in the previous topic and what I've just mentioned in terms of some statements that I will ask you to help me fill in the missing spaces or in the blanks. And at the end of it all, then we shall be able to explain some of these facts. So, as I've just said, I would like us to try and fill in the missing statements in the following questions, which will be trying to assist us recap what we did in the previous topic and what I've just mentioned earlier on in this topic. So statement number 1 asks us to have the particles of matter are always dash. This is a recap of what we did previously. He's asking us, the particles of matter, how are they? So the particles of matter are always mobile. They are always mobile. They are always moving. Though at different levels of movement, but they are always moving. They are mobile. For solids, they will move by vibration. For liquids, they move by rolling over each other. And for gases, they move by colliding and randomly filling every part of the container that is holding the substance, which is matter. The second statement is asking us, particles in a solid simply dash in their fixed position. From my previous statement, I've already answered that by saying particles in solid state vibrate in fixed position. That is the way solids move, vibrating in fixed position. The third statement is particles in liquids dash over one another. It is also a way of moving in liquids. Particles in liquid state roll over. That is how they move. They don't move by vibration, but they move by rolling over each other. In fact, that's what makes it possible for a liquid to roll over each other to go and occupy every part of the container where it can be held up to that level, not spreading to all other parts of the container like a gas. The next statement is particles in gases move dash. Particles in gases. So the particles in gases move randomly. They move randomly, and this is why particles in gases state will always move to go and cover every part of the container. As they are moving randomly, they move randomly to any space, not where there is no space. They will always move randomly towards any space, and at the end, they cover all the available space the container holding the gas is having. The next statement is, these ideas are known as the dash, then dash. The ideas I've just talked about, how the solid moves, vibration, how the liquid moves, rolling over, and how a gas moves randomly. These ideas are known as, or are called, kinetic theory. This is the kinetic theory. Talking about movement in solid, movement in a liquid, and movement in a gas is what we call kinetic theory. The next one is, when matter is cooled, its dash move more dash. When matter is cooled, here we are looking at temperature being reduced. When the matter is cooled, temperature, heat is being withdrawn. When you add in heat energy, you are increasing temperature. When you reduce heat energy, you are reducing temperature. So the question here is asking us, if the temperature has been reduced, if that heat energy has been withdrawn, what will happen to the matter? So when matter is cooled, its dash move more dash. So when the matter is cooled, its particles move more slowly. Its particles. These particles are in solid, liquid, and gas state. So when you are cooling, you can be cooling a solid even further. You can be cooling a liquid further. You can be cooling a gas further. So it doesn't matter the type of state of matter you are talking about. But in general, you are talking about matter. So when you cool the matter, when you reduce that temperature, you make the particles to move more slowly. The next statement is about, when the matter is heated, we say that its dash move more dash. This is the opposite of what we have just talked about. The opposite of reduction in temperature. Removal of heat energy. So here you are adding in heat energy. You are increasing the temperature. And when you increase the temperature, you are adding more kinetic energy to the particles. It doesn't matter the state of matter. Irrespective of the state of matter, the particle in that state of matter will have acquired more kinetic energy. And as we said, temperature as a measure of kinetic energy, and also as a measure of how fast or how slow the particle moves. So here we are increasing the temperature. This makes the particles to move more faster. So here we can answer the question by saying that the particles of matter, when matter is heated, we say its particles move more faster. The opposite of its particles move more slowly in our previous question. The next statement is we interpret the amount of movement of the particle of matter as its. How do we interpret movement of particles of matter? We have just said that irrespective of the state of matter, particles move. So the question is asking us how we interpret the amount of movement of the particles of matter as its kinetic energy. The more it moves, the higher the kinetic energy. But you can also interpret it in terms of temperature, whereby we say if the particle is moving very fast, then the temperature is high. If the particle is moving slowly, then the temperature is low. But as you can see, it's like there's a very thin membrane between temperature and kinetic energy. So you can interpret the movement of a particle in terms of how much kinetic energy the particle has, and that is, if it is moving very fast, then it means it has more kinetic energy, or sorry, and if it is moving slowly, then the kinetic energy is low. Or interpret it in terms of temperature, whereby if the movement of the particle is faster, then it shows that the temperature is high, or if the movement of the particle is slow, then the temperature is low. So in filling up that space, you can use either kinetic energy or temperature. But going by the topic of the day, then the best to use, which is carrying the umbrella of movement and kinetic energy, is temperature. So you can say we interpret the amount of movement of particles of matter as its temperature. The next is the particles of matter are held together by dash, which is dash in strength. The particles of matter are held together by dash, which is dash in strength. All these particles, solids, liquids, and gases, there is something in between the particles, and that is a force that holds the particles together. In solid state, the force that holds the particles together is much stronger, which is then followed by particles in liquid, and the particles in gases are the ones that are held much weakly by the forces. In fact, you may think that particles in gases are never held by any force of attraction, and that's wrong. They are held by very weak forces of attraction, which easily get broken, and that's why the particles can move randomly to all directions. But there is some slight force of attraction holding the particles. So in filling up the gap, we can say the particles of matter are held together by forces which vary in strength. Forces which vary in strength. In a solid, the highest, and in gas, the lowest. The next statement is about particles in a solid are held together dash. Particles in solid are held together dash. Particles in solid are held together strongly. It's comparative. We are comparing a solid, a liquid, and a gas. So in comparative answering, you say particles in solid are held together strongly, meaning that we also have another one which might be held together, yes, but in a lesser, a stronger way. The next one is particles in liquids are held together dash, then dash, than those in solids. So they are comparing. They are saying than those in solids, comparing a liquid and a solid. And the question is, particles in liquids are held together by dash forces. But this force, they have to be something in relation to solid weaker than, forces weaker than. And that is how we can feel in that space that particles in the liquids are held together by forces weaker than those in solids. And that's why you will find that particles in a liquid can be able now to be free to roll over each other, while in the solids they can only manage to vibrate in fixed positions. The next one is particles in gases are dash held together. Particles in gases are dash held together. So we are talking about particles in gas. How are they held together? We just said all particles must have a force in between them. The difference being the strength. So particles in a gas are the ones that are weakly held together. So we can say particles in gases are much weakly held together, because you are comparing weakly or less strongly held together. And going by the statements we have been using for the upper one, we can use less strongly held together because we have been using the word stronger. So particles in gas are less strongly held together. Another statement asking us, gas particles at 100 degrees centigrade have dash energy than liquid particles at 100 degrees centigrade. This one takes us back to the opening statements I gave, where we looked at the energy in two states of matter that are at the same temperature. The question is asking, gas particles at 100 degrees centigrade and liquid particles at 100 degrees centigrade. We are talking about the same temperature, but a gas and a liquid. So the question goes, gas particles at 100 degrees centigrade have dash energy than the liquid particles at 100 degrees centigrade have more energy. Particles in gas state at 100 degrees centigrade will always have more energy than particles in a liquid state at the same temperature, which is 100 degrees centigrade. Now, before introducing this statement, I said that we need to answer some of these statements to assist us explain some aspects that we commonly encounter or see and wonder why. And one of the aspects is the last question we have just read. How come we have just said that gas at 100 degrees centigrade has more energy? The answer was more energy, has more energy. Has more energy than liquid at the same temperature, which is 100 degrees centigrade. Let's be able to look answer this question in terms of temperature causing variation in movement of these particles. Temperature causing variation in movement of these particles. And these particles in liquid and particles in gas. At 100 degrees centigrade and at sea level, if we look at a liquid like water, then we can say whatever will be happening is boiling. At 100 degrees centigrade, if it is water at sea level, whatever will be happening is boiling. And what is boiling? Boiling is just a process of turning water liquid into water gas, which is steam, turning water a liquid into water a gas, which is steam. And this is achieved by breaking the bonds, breaking the forces that holds the particles in this water, breaking the forces, weakening them, forces that hold the particles in water, so that the particles in water can be left free to move far away from each other, making it appear as steam, which is a gas. Steam is a gas. It's only that it is called steam to show a gas of water. Otherwise, it's just a gas. So it has been achieved by breaking the bonds. Now the question comes in. What causes the breaking of the forces? What causes breaking of these bonds? And that is the increase in temperature. So you'll discover that, and in case you can be able to carry out this experiment, you can find a thermometer wherever. This can be done in a school setting, home setting, so long as you have a thermometer. You discover the boiling temperature of water at wherever point you are, because as I said earlier in the previous lesson, that water does not always boil at 100 degrees centigrade. It only boils at 100 degrees centigrade when you are at sea level. But when you move higher up, higher than the sea level, the temperature drops. So you can boil water at 90, 98, 96, even 70 degrees centigrade. If you go high up into the mountains, temperatures at which water will boil might go up to as low as 50 degrees centigrade. The same applies to when you go to areas lower than the sea level, then temperature, the temperature at which water will boil will be higher than 100 degrees centigrade. So, looking at the temperature at which water will boil at wherever point you are, then check on the thermometer as you continue heating the water. Check at the level the mercury reading will be on your thermometer as you continue heating the water. That is, as you continue adding in heat energy. And as we know, you add in heat energy, you expect the temperature to rise. What you will observe will be the temperature will remain constant. The temperature will remain constant. Why? Because as you are heating, and this is our thermometer, if this is our boiling point, which I'm assuming you are not at sea level, let's assume the water boils at 97 degrees centigrade. This thermometer has been dipped in boiling water. This boiling water is still being heated. So heat is continuously being added in this water. The water is boiling. So that is boiling water. It will be found that the mercury reading will not go beyond 97. It will remain at 97. But we are still adding in more heat energy. Where is this heat energy going to? If it cannot make the temperature go higher than the boiling temperature, which at this point I'm assuming is 97 degrees centigrade. You can take it at any temperature. You can still use 100 degrees centigrade, but I'm choosing 97 because I assume where you are is not at sea level, and you may want to do a test of what I'm talking about. So the mercury will remain at 97, though you are still continuing with your heating. The energy you are introducing into the water through the heating will not be used in raising the temperature of the water, but it will be used to break the forces that hold molecules in water, liquid state, make the particles move far away from each other now that they have more kinetic energy and they are moving much faster. They move away, they break off, move away, and in a faster manner as steam. That's why the temperature remains constant. This one is also used in explaining the aspect of the solid at 0 degrees centigrade and liquid at 0 degrees centigrade. At temperature, we said for water it will be melting temperature. The same explanation can be applied, whereby if you have a solid, now this, if you can assume this is a solid, now we take this one as a ice cube, ice cubes, that is water in solid state. You are heating. When you heat, these ice cubes will do a process called melting to form water, which is a liquid. But the mercury will be maintained at the melting temperature, which you can take here to be 0 degrees centigrade. But remember, you are still heating. Why? The answer is, as you continue heating, just before all the ice cubes melt, just before all the ice cubes melt, the addition of heat energy only does one thing: break the bonds, weaken the bonds in the ice cube, which is a solid, in the ice cubes, which is a solid, so that the molecules of water in ice state can now break loose a little bit to be able at least now to roll. Because in ice form, they can only vibrate, solid state. But as you add in heat, it loosens, it weakens the forces until these particles are now free at least to roll over each other. Though the particles will be close, still close by, but they will be free at least to roll over each other. As they roll over each other is what you will be seeing as now water being formed, what we call melting. And in fact, you will see if this is our ice cube. As it melts, you will see droplets of water rolling down, just to confirm to us it is true. In a liquid state, particles roll, because if you are rolling, it means you are going down. So you will see the solid ice cube will still be in that position. But as it melts, the part that melts rolls down. The part melts, rolls down. Because of that, since the whole ice cube hasn't melted, any addition of heat energy will not go into increasing the temperature, but will only be used in breaking or weakening the forces in the solid to form a liquid, a process called melting. Breaking or weakening forces in water to form steam in a process called boiling. Weakening forces in ice to form water, melting. Weakening the forces in water, forming steam, boiling. And at boiling stage and melting stage, the temperatures are constant. Another explanation we need to make, an account of all these observations, is accepting that what we know as temperature or heat energy is a measure of average kinetic energy, or that's motion of the particles of matter, explain how this leads to the idea of an absolute zero temperature. The question is asking us, we have just said that temperature is a measure of kinetic energy in particles. Temperature is also a measure of motion of the particles in matter. How then can we apply this temperature to explain the aspect of absolute zero, as was explained in our previous lesson when we were looking at the development of the kinetic theory of matter? In the development of kinetic theory of matter, we looked at one scientist, Lord Kelvin, who looked at the temperature scale that was being used by then, which is still is applicable at the moment, that's the Celsius scale, and saw it to be unable to explain some fact. To him, he expected at 0 degrees centigrade, everything should be zero. And particularly for gases, the volume of the gas is supposed to be volume of any gas. To him, at 0 degrees centigrade, volume of any gas was supposed to be zero. But that was not the case, because even in your country, other countries, you may find that temperatures go as low as 0 degrees centigrade in some areas, but still people continue breathing. Animals breathe, plants exchange gases. How? This shows that the gas at that temperature, which is 0 degrees centigrade, is not zero. It is being occupied, but at a particular volume, as was also explained by Charles Law, a scientist called Charles, who talked about the relationship between volume of a gas and temperature. So the only thing you will have done here is you will have reduced the volume of this gas by going to 0 degrees centigrade from our normal temperature of 25 degrees centigrade, which is called room temperature. You will only reduce the volume of a gas, but it will not go to zero. But Lord Kelvin really wanted a point where gases can achieve a zero volume. Then he had to look at it by creating another scale, what we call the Kelvin scale, which can be represented as so we are having volume of gas. It can vary from 0 to any figure up there, depending on the temperature. And here we have variation in temperature, but using Celsius scale. So at 0 degrees centigrade here, 0 degrees centigrade, you can see the volume is not zero, because 0 is at this point, but we are way above 0. Volume is not zero. But looking at this extrapolation, if you can use this as an extrapolated line, it is going to cut the temperature axis, which is the x-axis, at a point which, going by the plotting, at this point, volume of a gas is assumed to be 0. Is assumed to be 0. Why? Because going by how the gas was behaving from as high as maybe 100 degrees centigrade, as you are reducing the temperature 98, 99, 96, 90, 80, 70 until you reached 0 degrees centigrade, it was following a particular straight path, which we have taken to be this one. It was reducing. So following the same path, but now less, at a lesser temperature than 0 degrees centigrade, it will go until it cuts the temperature axis at this point. So at this point where it cuts, the temperature axis is what we call 0 Kelvin or absolute 0. Now, using temperature, kinetic theory of matter, using temperature, which takes us to kinetic energy, and which takes us to how fast particles move. Let's see how we can explain why gases at this temperature, which is now in Celsius scale, is negative 273 degrees centigrade. The volume is assumed to be 0. The volume is assumed to be 0. Why? Because as you reduce the amount of heat energy in a particle, you reduce the kinetic energy in the particle. And as you reduce the kinetic energy in the particle, you reduce its speed of movement. And as you continue reducing, again the speed continues reducing. It's like you are applying brakes to a moving vehicle. The more you apply the brakes, the lesser the movement. And if you continue doing so, it will reach a time where it will stop. So, looking at a gas, because this one can only be explained using a gas. So, looking at a gas where the particles were far apart because of very weak forces holding them, as you reduce the energy in them by reducing the temperature, the particles start moving closer to each other. Meaning that you are reducing the volume. Move closer, reduce the volume. Move closer, reduce the volume. It will continue this way until you will find that these particles, which we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 particles, all moving towards a center point. 10 particles. So we can have the same 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's still 10. But look at the space they have occupied. The space is smaller than this. This is being achieved because the particles are losing energy because of reduction in temperature, moving much closer. Again, reduce the temperature. They will move much closer to each other. We get a different third option. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But they are still in gas state. But look at the volume they have occupied. So this volume is reducing. This can go on until you will find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are so close. They are 10, but they are so close. At this point is where we now assume the volume of that gas is being assumed to be 0. Because realistically, you cannot achieve 0. If it was a gas, it is matter. And matter, we said, it must occupy space. Maybe the whole of these 10 particles were occupying the whole of this room. We cannot judge them by how much they were occupying, that we have a lot of gas. No. Because gaseous particles will occupy everything. But we can also not just assume it is 0 at that absolute 0. Because since it was matter, it must occupy space. So even if it will be too small, but it will be occupying space. But for mathematical case, we always assume at negative 273 degrees centigrade or 0 Kelvin, which is called absolute zero, the volume of a gas will be zero. And how we achieve it is by reduction in heat energy, which leads to reduction in temperature of the gas, reducing the movement of the particles, making them move closer to each other, and the further you reduce, the further they move much closer to each other until they form a very tiny particle of the gases. A very tiny particle of the gases. Looking at these 10 particles of a gas, like for example, oxygen gas. Oxygen is a combination of 2 oxygen atoms. Look at how small an atom is. An atom is very small, smaller than a cell. But a cell, we cannot be able to see it using our naked eyes. We need a microscope. But inside that cell, we have so many organelles. And those organelles are made of so many atoms. So you can imagine how small an atom is. And an oxygen molecule is only 2 atoms, very small. Now we are talking about 10 oxygen molecules. They will occupy the whole of this room. When you freeze it to negative 273 degrees centigrade, they will form a solid, because they will have moved to a liquid, then to a solid, because you are removing the heat energy. In solid form, they will form a very small particle that you will not be able to see. You will require an electronic microscope to be able to see. And that's why we say we assume its volume is 0. Because you require an electronic microscope to see the particle that will have been formed from the so much gas you are feeling at that particular time. The other aspect that we need to explain is consider 4 different pictures of water in this state. We have water in a beaker. And this water is boiling. So this one is boiling water. Then we have ice blocks or ice cubes. We can have an ice cube here. Or blocks. A third one is shower water. You have a shower. It has so many openings. So in this shower, there are splashes of water coming out. Then the fourth one is steam. Maybe you have an open container which is having very hot water. So you have this steam. This one is water. But remember, this is running water in a shower. All of these are water, but water in different states. So the question is, consider the 4 diagrams I've just drawn. In which picture or in which diagram will the water particles be moving most slowly? Justify your answer. Most slowly. Most slowly, most comparative. It means all these diagrams are giving us water that is in motion. The only difference is at what level of motion. And the level of motion is based on how much temperature, at what temperature. So let's interpret first of all this in terms of temperature and see which one is at a higher temperature and which one is at a lower temperature, because temperature is the one that dictates movement here. Starting with the boiling water. Boiling water, it means this is at 100 degrees centigrade. But remember, it is water, boiling water, not steam, boiling water. So this is 100 degrees centigrade. This is ice cubes. Ice cubes, it means water in solid state. This one tells us that either we are talking about 0 degrees centigrade or less. Because the water at 0 degrees centigrade, it has two options: either to be in a liquid state, that is after having melted, or be in solid state, that is in ice form. So it is either at 0 degrees centigrade or low. Water in a shower, it is water in a shower. Whether it is cold water or warm water, but being in a shower, this is at a temperature where you are able, you should be able to use the water. So though this is water and this is water, but this one being in a shower and this one is boiling water, this one should be at a lower temperature than this one, because it is in a shower, even if it is water. So movement in boiling water will then automatically be higher than water in a shower. I will come in to explain later, because it can be a bit confusing. You will look at it that this is boiling water but stagnant in that container, and this is water in a shower. It is moving, it is coming out. Why should I say movement here is higher than this? There's a point I will come in to clarify on that, but the point here is look at it in terms of temperature only. The temperature here is higher than this, so movement here will be higher than in water here. Then we have steam. We are not interested in this water. Our interest is in steam. And for us to create steam, then we require 100 degrees centigrade, just like this. This one comes in again, similar to what we answered earlier, comparing the amount of energy in particles to two states of matter that are existing at the same temperature. So those are existing at the same temperature, 100 degrees centigrade, but this one being water and this one being steam, steam has more energy because it has acquired that extra energy. You are heating the boiling water, which made the particles to break off and become steam. So I've only explained why this should be having higher movement than this one the least movement, and this one being more than this. But now let's look at the question. In which diagram will the water particles be moving most slowly? And the answer is in the ice cubes. In ice cubes, the movement of the water particles in the ice will be the most slow. Reason being, in the ice, being a solid, particles have lost energy, because for you to form ice, you lost energy. So it has very little energy for them to move. And as a result, they only vibrate. So to justify the answer is, to form ice, you lower the temperature. And by lowering the temperature, you reduce on the movement. And by reducing on the movement, you make the particle to be static. And being static, the only type of movement that will be left will be vibration at that fixed static position. Because we are talking about temperature in relation to movement. The next question is, in which diagram will the particles have the most kinetic energy? Justify your answer. The most kinetic energy. In the opening statement, I said that temperature is measured in two ways. Look at the amount of kinetic energy the particle has, or look at the rate at which the particle is moving. For the first question, we have been looking at temperature in terms of movement. where we have said this one has the least movement. In this present question, it is asking us to look at kinetic energy, which is the other factor, kinetic energy. So, in terms of kinetic energy, this one being the least, it is followed by this one. Being water and this one being water, this one is lower than this because this is water but at 100 degrees centigrade. But this is water at a temperature lesser than 100 degrees centigrade. So this one in terms of movement is second slow to this. Then this one is followed by the water in the shower, because though it is water, is at 100 degrees centigrade. Then the one that is the highest is steam. Steam is 100 degrees centigrade, water is 100 degrees centigrade. What is the difference? The difference is in the steam, more heat energy was put in to break the molecules in water, to break the forces in the molecules in water, so that the molecules can break off and move away as steam molecules. So the one that has the highest kinetic energy is steam. The one that has highest kinetic energy is steam. And the answer is, to make steam molecules or to make steam particles, more heat energy was used. The one that took the water to 100 degrees centigrade, and the more that was added in to break now the forces holding the particles in liquid to break off to form particles in gas state, which is steam. Lastly, where does the speed of the water particles in the shower water fit into this? And this is the point I said I will come in to explain later. Look at the water as it comes out of the shower. It comes out at a relatively high speed, because remember, this water is coming from maybe a tank that has been raised up there. Because of the potential at which the water is flowing, it will come in very fast. So how do we fit the movement at which this water is coming out of the shower? That one is fitted in the rolling nature of the particles in water. Rolling nature, not the movement of the particles. Movement of the particles of water is because of temperature. That is how much they will move from one place to another. But the streaming out of the shower is because of water molecules being able to roll over each other. Maybe to help understand this well, take an example of a thicker liquid like glue. Be pushed to come out of this shower. You will find that though it will come out of the shower, but it will not come out as fast as this water. Why? Because the molecules in that glue, being thick, they don't roll over each other as fast, because they are almost tending towards the solid. So they will roll over very slowly. And in the process, as it streams out of the holes of the shower, it will come out very slowly. The other way you can look at it is, how about when this pipe that brings in the water to the shower is frozen? Meaning that you turn the water that is coming in into ice. Will the water come out? The answer is no. The water will not come out, because that water will no longer be water as a liquid, but it will be water as a solid. And as we know, solids are closely packed together because of stronger forces holding the particles together, and as a result, there is no movement. It is only vibration. And since there is no movement, which is in nature of rolling over each other, the water will not come out of the shower. So we only fit the movement of the water streaming out of the shower very fast as rolling of water molecules or water particles or liquid particles, because the water is a liquid, as rolling and not movement in terms of how much temperature the particle has. This water, whether it is at 0 degrees centigrade, but it's water, or this water is at 99 degrees centigrade, but still water, it will stream out at the same speed. Water at 0 degrees centigrade, but water, and water liquid, and water at 99 degrees centigrade, but water, will still stream out at the same speed, showing us that streaming out from a shower has no direct link with temperature and movement. Looking at what we have been explaining, it has given us a basis on explaining the various aspects and concepts we always encounter, like the issue of constant temperature, different states of matter. This can be expressed diagrammatically as follows, which will be kind of summarizing all that we have done. Starting with the water in solid state, assuming that we are maybe at a -5 degrees centigrade. As you increase heat energy, the temperature also increases. So at this point, I can call it from point A to point B, which is at the negative. Maybe let me use this Cartesian plane this way, so that this one is a negative temperature. So maybe we are starting at -5 degrees centigrade. So as you move from -5 degrees centigrade to 0, at this point is 0 degrees centigrade. This one is temperature. The temperature is increasing. How? You are heating. So you are adding in heat energy. So at -0 degrees and -5 degrees centigrade, -5 degrees centigrade, as you heat, temperature will increase from -5 to 0 degrees centigrade. But it will still be in solid state. It will still be in a solid state. But once it reaches 0 degrees centigrade, this is 0 degrees centigrade, at that point is 0 degrees centigrade, the temperature remains constant. The temperature remains constant. But remember, you are still doing what? You are still heating. What is happening? The heat energy you are putting in is being used to break the forces holding the solid water particles, making them break free to be able to roll over each other, a process we call melting. So the solid melts. We are now turning a solid to a liquid, a process we call melting. The heat energy is being used to break the forces that holds the particles in solid into being free so that they can roll over each other to melt, to form a liquid. From this point, you continue heating. As you continue heating, so you are heating, the temperature will rise from 0 degrees centigrade to a point 100 degrees centigrade. This is at sea level, so we use 100 degrees centigrade. So at this 100 degrees centigrade, the temperature again becomes constant, just like here. Temperature here is constant, temperature here is constant. But remember, you are still continuing with the heat. What's happening? The heat energy being added in is being used to break the forces holding the liquid molecules, because this one is now a liquid. After melting, this is now a liquid. So the forces holding the liquid molecules close together so that they can only roll over but cannot break free. Molecules can roll over but cannot break free, are now being broken and allows the particles to break free into a gas. So this one is gas state, whereby the liquid is turning into gas, a process called boiling. So what we are having is boiling is taking place. You boil, change liquid to gas. What is important in this diagram is at this point the temperature is constant. Energy is being used to break the bonds and not to raise temperature. Energy is being used to break the bonds or the forces and not to raise the temperature. But at point CD, and point AB, the temperature is the heat energy is being used to raise the temperature. The heat energy at AB and CD is being used to raise the temperature. BC, DE, the heat energy is being used to break the forces holding the molecules together so that they can change from one state to another. That marks the end of our lesson today. Until next time, thank you.